Searching for a specific item inside a list or an array is one of the most fundamental and common operations in programming. The simplest and most intuitive way to do it is called sequential search, also known as linear search. You start at the very first element, compare it with the target you're looking for, then move to the second element, then the third, and so on, one by one, until you either find the target or reach the end of the list. Because you may have to check every single element, the time complexity of sequential search is O(n), where n is the number of items in the list. In the worst case, when the target is at the very end or doesn't exist at all, the algorithm has to examine all n elements. And that makes linear search extremely slow when you're working with large data sets. Imagine searching through 1 million records. You could end up doing 1 million comparisons. Not very efficient, right? Fortunately, there's a much smarter and faster approach, but only if one very important condition is met. The data in your list must already be sorted in ascending or descending order. This is the essential prerequisite for binary search. If the list is not sorted, binary search simply cannot work correctly. So, assuming your list is properly sorted, binary search completely changes the game. Instead of checking one element at a time, it uses a divide and conquer strategy. It repeatedly divides the search space in half with every single step. Here's how it works in practice. You begin by looking at the middle element of the sorted list. If it matches your target, you're done. You've found it. If the target value is smaller than the middle element, you know the answer must be somewhere in the left half of the list, so you completely discard the entire right half. If the target is larger, you discard the left half instead. Then you repeat the same process on the remaining half. Find the new middle, compare, and halve again. Because each step cuts the remaining search space exactly in half, the number of comparisons needed grows incredibly slowly. This gives binary search a time complexity of log n. That's dramatically better than the O(n) of linear search. Let me give you a quick sense of how powerful this is. For a list of just 1 million elements, linear search might need up to 1 million comparisons in the worst case. Binary search, however, only needs around 20 comparisons. Yes, just 20. That's the magic of logarithmic time complexity. So, whenever your data is already sorted, binary search transforms a slow, brute force problem into an elegant, lightning-fast solution. It's one of the most important and widely used algorithms in computer science, and mastering it will help you write much more efficient code in almost any project you work on.